Hello everyone, my name is André Ferreira and I'm part of the Faking It team. Today I will present our solution entitled Achieving over 10 times faster sample generation with conditional denoising diffusion. In this presentation, we propose a solution for both task 8 and 9 based on diffusion models. For task 8, the goal is to generate a missing MRI modality knowing the other 3. And for task 9, the goal is to replace the unhealthy region of the brain with healthy tissue. For the missing modality task, the dataset is composed by the 4 modalities from both adult glioma and brain metastasis datasets. For the inpainting task, the dataset is based on the adult glioma dataset, but only the T1 modality is available, as well as the dilated mask of the tumor and the mask of a random healthy region. Our network is based on the Sweeney net, which has convolutional layers on the top layers and attention mechanism on the deeper layers. We call it variable step DDPM, as we can customize our pipeline to work with any number of time steps. Both tasks have similar training and inference processes. For task 8, the condition is the known modalities and the volume full of ones instead of the missing modality. For task 9, the condition is the voided volume and the respective healthy mask of the region to inpaint. The training process took 15 days to finish. We use a data splitting of 90% for training and 10% for validation, batch size of 4, and a sliding window. We also normalize the data using z-score of the foreground followed by linear normalization to -1 and 1. To make our solution more efficient, the diffusion process is optimized to 25 steps using pixel-wise metrics such as mean, squared, and absolute errors, structural similarity, and the crucial variational hour bound. For the inference, we only need a GPU with less than 2 GB of VRAM, and each case takes less than 2 minutes. However, it depends on the graphic card, of course. As results, we can see that using global statistics for z-scoring with regular sampling produced the best results for task 8. For task 9, the best solution also used the regular sampling. This is expected, as the diffusion process trained with variational lower bound is optimized to work with the 25 steps. We also noticed better performance when linear normalization to -1 and 1 was used. Visually, we can see some artifacts created by the sliding window approach. This could be solved with Gaussian blending. However, this was producing worse quantitative metrics. Therefore, we decided to keep the blending by averaging. In conclusion, we saw that using linear normalization after z-scoring improves stability, therefore the results. For the diffusion process, 25 steps were enough, although we didn't test for less steps. We also tested for 1000 steps, but without any improvements. This new proposed solution is 10 times faster and up to 28% better than the solution proposed in 2024, and only needs less than 2 GB of VRAM to run the inference. The main downside is the use of sliding windows, which creates artifacts at the edge of the windows. Thank you very much for your attention.